All right, so with the modeling, with the exponential loss function stage 2, we are going to be looking at radioactive decay, heat diffusion, the pH scale, and the loudness of sound. So a big application is this radioactive decay, this half-life. When you have a radioactive substance, it decays by spontaneously emitting radiation. Okay, so when you have the rate of decay, that is going to be proportional to the mass. And this is very similar to population growth, but the mass is going to decrease. So it decreases, and the physicists express this rate of decay in terms of the half-life. Okay, so if you have a radioactive substance with a mass of m sub 0 and a half-life of h, then the amount remaining at time t is given by the following equation, which looks almost identical to what we did yesterday. Okay, the only difference is you are going to have a negative exponent. There we go. Okay. So m of t equals m sub 0 times 2 to the negative t over h. Because it's the half-life, this negative here, remember how if you have a negative exponent, you put it under 1. So that is equivalent to having the half. Okay, and then we also have a second model. Again, this is very similar to what we did yesterday. That is similar to the PERT equation. And then notice they give you that value for R. So the R is equal to the natural log of 2 divided by H. Okay, you will have a formula sheet for your chapter board test that is on Friday. Okay, so you are going to see these formulas on there. You will just need to know how to use them. Okay, so I'm going to give you some time to do example 1, part A and part B. In part A, we are going to be finding a function of the form m of t equals m sub 0 times 2 to the negative t over h. And B, you're finding a function of the second form. Okay, so in both of these, you are finding a function. Both of the function is going to be after t minutes. Okay, so using the information given and what you know from yesterday, I want you to do part A and part B. Okay, and then I'll just call on you guys to help me in a minute. And then while you guys are working on that, I am going to pass out just a little square of graph paper that's going to be for part B. So just take one and pass it down. All right, John, tell me what you got for the first part. What'd you get for your first equation? Nice. Okay, so you're plugging in your 1.94, which is your half-life. That goes in for H, okay, not for T. It is a unit of time, but it's the half-life. And then they give you the 1,500 atoms to start. Okay, it does say T's in minutes, so it's okay if you don't specify that. And then when you go to part B, you have the M of T equals 1,500. And then it's e to the negative RT. So you are going to have to find R using your equation right here, the natural log of 2 divided by H. So we are going to do R equals the natural log of 2 by H. So the natural log of 2 divided by 1.94. Okay, and just like we've been doing with the logs, we are going to round that to 4 decimal places. Okay, so you get 0.3573. Okay, so your M of T is going to be equal to 1,500 e to the negative 0.3573t. If you want to leave it as an exact value, you can. You can leave it as the natural log of 2 over the 1.94t. Okay, and then when you get to part C, it says approximate the number of atoms remaining after 5 minutes. So you are just going to plug in 5, and you get to choose what model you're going to use. Just show your work for whatever model you have, which one you're plugging it into. Okay, because you are going to have multiple options there. So T is equal to 5. I'm going to show you the difference in the answers of all 3. Like I said, you can just pick one. And then once you've calculated that, I want you to set up part D. Part E is the graph that's going to go on your sheet of graph paper here. So you don't need to say room for that, okay? And for part C, you can round to the nearest atom. 3 of these into the calculator so we can look at the table and compare. So it doesn't matter which one you choose. This is part A. These are the 2 from part B. You go to your table for 5. Okay, each one is going to round to 251.3. If you look at the nearest tenth, like I said, we are going to be rounding to the nearest whole number. So you get to choose what model. Okay, you can choose any of those. All you have to show me is which one you chose by plugging that into your equation. I like the one with E in it because that's the one I usually like to solve with. Okay, so when I do the calculation, I'm plugging in 5. And then, Jack, how many atoms did you get for this? Yep, 251 atoms is correct. Okay, and you are following your normal rounding rule, so if it's 0.4 or below, you keep it, and then 0.5 or above, we'll round up. All right, and then Spencer, for part D, will you tell me how you started that equation? Yeah. Yes, okay, so you can choose your model. Doesn't matter which one you use, okay, but you are going to set it equal to 1. So I'm going to write out my work for this one. In our next example, I am going to show you both values, both ways to solve. Okay, I'll also tell you what you should do if you chose the other model. Your steps are going to be very similar. You are always going to isolate the exponential function. So in this case, I want to get E by itself. Okay, and no matter which function you use, you're going to divide by the 1500 first. If you choose the model with E, you're going to take the natural log. If you choose the model with a base of 2, then you're going to take the log base 2. Either way, you're going to get a value that is going to be brought down by the power law, and then you're going to divide for this model, so negative 0.3573. Okay, I should be able to follow your work very clearly. Okay, so you need to make sure you're showing the log from both sides. Okay, I am going to be assessing that you know how to use those inverse functions. And then if you did the log base 2, do you see how you have a fraction here? So when you go to solve and you have a denominator, you're going to have to multiply both sides by the denominator. And then you can divide by -1, or if you want to multiply by the negative at the same time with the denominator, that would be another option. All right, so this is going to be 20.5, and we are always going to include the units because they are going to change from problem to problem. Okay, so the T here is going to be 20.5 minutes. If a problem doesn't specify what you are going to round to, you can choose. You just need to make sure that you're paying attention to your rounding rules. Okay, and then on your assessments, they will tell you what to round to. All right, and then as we start our graph, know again that you can choose what model you want to graph. They are all going to be very similar. And before I start my graph, I like to assess what kind of point values I have so I know what I want my scale to be. We know our starting value. How many atoms did we start with? 1500, right? So I'm going to have to make a graph that goes up to at least 1500. I already have my y equals in here, so when we go to the table, sorry, I'm going to start at 0, and then I'm going to look and see what's happening here. So yep, I have 1500. At 2, I'm at 734. Generally, I will round to the nearest whole number because when you're dealing with numbers this large, okay, a 0.4 isn't going to matter. Okay, so I have 359. At 6, I'm at 176. Okay, and try
try to at least get 5 points. They don't have to be the exact same points that I'm doing. As these numbers are getting like a lot smaller, bless you. Okay, you're going to know that they're approaching a value that is close to 0. Okay, so I'm going to see, I have to get up to 1500. I'll see if I have enough space. I don't think I'll have enough space on this one to go by ones. So I might have to go by 200s instead of 100s. I think maybe I could. It would be way up here. 1, 2, 3, 4, 5, 6. Yeah, it'd be right there. Should I go by 100? Can you guys fit the 100s on there? Do you have to go by 200s? Are we counting our squares to see? I don't think all of you are going to be able to have 15 spaces. All right, I'll go by 200. Okay, and then here I'll go by 2. So 2, 4, 6, 8. Okay, and again, if you can fit the 100s on there, feel free. So 200, 400, 600, 800, 2,000, 1,200, 1,400, 1,600. It's not going to be more than that. Okay, so at 0, 1,500, I'm directly in the middle there. At 2, I'm at 700, so that would be about halfway, a little more than halfway. At 4, I'm at 359, so under 400. At 6, I'm close to 200, and then you can see these values are getting closer and closer. Like I said, as long as you have 5 points on there, that should be good enough to make your curve. Okay, so I'm putting 5 of my points from the table on there, and then I'm connecting this with a curve. And it's just going to get closer, so I'm going to put my arrow on this side. All right, and then I will pass around the stapler. So if you just want to put one staple here, there'll be like a nice little booklet. And voila, there's your book. It's like a fun little story. I'm just going to put E on your graph. All right, so as I am passing that around, in example 2, we are going to do 2 methods. So I want you to start with method 1, which is using that first function to solve. Okay, and then in method 2, you are going to use the PERT equation to solve. Okay, so I'm going to give you some time right now to do that. And then you can just pass your stapler around. I don't know.
happening there? I guess after 2 classes that was fixed.
All right, if you are having trouble getting started, okay, we need to start by reading the problem. I would highlight some of those key values that they gave us. And let's plug them in. Okay, you guys have the skills to do this. All right, so when you are setting this up, it says the half-life is 28 years. All right, so Victoria, where'd you plug the half-life in for? It's your H, yep. And then Jackson, where'd you plug in the 50 milligrams? The M sub 0 is going to be your initial value, so great. And then that means your 32 is going to be plugged in for what? What did you guys plug your 32 in for? Your what? M of 2. Okay, so 32 is going to equal 50 times 2 to the negative t over 28. So we start dividing by 50. If you get a nice decimal there and you would like to write it as a decimal, feel free. I don't even go to my calculator until I'm ready to do the log, so I keep it like this because I don't like going back and forth. All right, and then on both sides, you're going to take log base 2. If your calculator does not have the change of base, you can use your change of base formula, which would be the log of 32 50ths divided by the log of 2. Okay. If your calculator doesn't have that change of base, then you can still take the natural log here, or you would be able to use method 2. And then your final step, if we want to get t by itself, Logan, what are we going to do to both sides in this one? Yes, you do. You want to get t by itself? So we already did that, so what do we have to move over here? Yeah, so you can times 28, then divide by negative 1.
Or if you'd rather just multiply by negative 28 here, you could do that as well. Okay, so if you have a fraction, you're always going to multiply by the what? Oops, I don't want the log. I want the log base. Okay, if you have a fraction, you can always multiply by the what? Denominator. Great. Okay, so you get 18.0 here, or about 18. And then that's in years. So please make sure that you put the units in there. Okay, and then method 2, the first thing you should be doing is finding the r. So that's where you do the natural log of 2 divided by h. Okay, so that is here. Natural log of 2 divided by h. Okay, and then we're going to plug that into our equation. So you have 32 equals 50 e to the negative 0.0248t. Okay, and we've been practicing this a lot, so this might even feel tedious at this point. Like we know what to do and our mind is working faster than our pencil. That is a good thing because that means you understand this process. Once you have this e value, anytime you have that e by itself, you are going to take the natural log to bring that down. Okay, so you're using the power law, and then you're showing the division. I'm fine if you just leave this here and then show this division step here. What I'm really checking for is that I can see what you divided to get your final answer. So here I can clearly see that you're taking the natural log of 32, dividing by 50, dividing by 0.0248. And again, if we're rounding to the nearest tenth, that is going to be 18.0 years. Okay, if they asked you to round to the whole number, it would be 18. If they asked you to round to the nearest tenth, it would be 18.0. When you're doing your homework, you can choose what to round to if it does not specify. Okay? All right, now we're going to move on to Newton's law of cooling, which if any of you watch any like crime shows on TV, like I love Law and Order, and so the detectives will come in and be like, what was the time of death? Okay, you can use Newton's law of cooling to figure that out because it's based on the temperature of an object and the temperature of its surroundings. Okay, maybe you've even seen a show where a perpetrator tries to alter that, right? By throwing off the time to get the alibi out. So in Newton's law of cooling, we have a bunch of variables. Let's actually look at the equation first. It says T of T is equal to T sub S plus D sub 0 e to the negative KT. Okay, we know T is time. We know E is our exponential function. So let's figure out what the rest of these mean. This D sub 0 is the initial temperature difference between an object and its surroundings. And it says if its surroundings have a temperature T sub S, then the temperature of the object at a certain time t is modeled by this function. So the T sub S is going to be the surrounding temp. Okay, so that could be the temperature of a room, or if you're outside, it's just wherever the object is. Okay, we can think of the initial temperature of an object as T sub 0. Okay, the initial temperature of an object. And it says D sub 0 is the temperature difference between the object and its surroundings. So your D sub 0 is equivalent to the surrounding temperature subtracted from your initial temperature. Okay, so you take the temperature difference between the object and the surroundings. So it's very rare that they'll say, oh, your D sub 0 is this. Instead, they'll give you the initial temperature and the surrounding temperature. So I think it's helpful to think of your equation as T of T equals T sub S plus T sub 0 minus T sub S. So we're going to substitute. If D sub 0 is initial minus the surroundings, we're going to plug that right in there, and then e to the negative kt. In fact, in some textbooks, they show you this. They don't even have that value. Okay, so that is what your D sub 0 means. And it tells you that K is a positive constant that depends on the type of the object. K is called the cooling constant. So it changes for different objects in different conditions. So it's the rate at which an object cools. Whenever you are doing a problem with Newton's law of cooling, you are going to have to find K. Okay, you are going to have to solve to find your value of K. Okay, so in example 3, we have a cup of coffee that has a temperature of 210 degrees Fahrenheit. It's placed in a room that's 85 degrees Fahrenheit, which we laughed about earlier because people were saying that's a really warm room. I agree. And then after 20 minutes, the temperature of the coffee is at 140. Okay, we are going to find a function that models the temperature after t minutes. Okay, so in order to do that, we are going to have to find the cooling constant. Okay, so in part A, your first step is going to be to find K using that given information. So when you're doing these problems, you are always going to want to plug things in to find K. A good place to start is organizing the information that they give you. So if it says the coffee has this temperature, that's going to be your initial temperature. So the T sub 0 would be 210 degrees Fahrenheit. The temperature of the room is 85. That's the surrounding temperature. And then the last little bit of information they give you is that after 20 minutes, the temperature of the coffee is 140. Okay, what that means is when your T value is 20, the temperature at that time, which is T of T, would be 140. Okay, so based on that information, let's see if we can plug this in. Okay, so the T of T would be 140 degrees. Okay, then we have the T sub S, which is the surrounding, 85. And then it would be plus, and then we're going to do some subtraction here. So the T sub 0 minus the T sub S. And then this was at time T. So it was 20 minutes that had passed to get the 140. Okay, so you should have something plugged in for everything except for K and then your exponential function. So if we do that subtraction, the 210 minus 85, you can simplify it. We will simplify it in our next step. But when you are solving, you can't add these together first. You have to follow the order of operations. So multiplying would come before adding. That's why when you're solving, the first step is to subtract the 85 from both sides. Once you do that, you have an exponential function. We've been practicing these a lot, so we just have to solve that for k. Okay, so we're going to start by dividing both sides by 125. Okay, and see if we can finish that for k. The k value, we are going to round to 5 significant figures. So if you're already at that step, go ahead and round that. And then, like I said, I like to leave this as a fraction until I do my calculations. So you should be calculating the natural log of 55 divided by 125, and that whole value will be divided by -20. So if I'm doing significant figures here, that first 0 isn't going to matter. So I'll be 410, 49. Okay. All right, so we had to find a model. So your model is going to have these values plugged in. So we have t of t is equal to, our t sub s is 85. We're going to write the simplified 125 e, and then when you plug this in, because you have the negative in front, it'll be 0.04 1049 t. This is going to be your model. Okay, and then part B is asking you, what is the temperature after 25 minutes? So in that case, your value for the time is 25. You can do a simple calculation there. So we're just going to plug it into this model. Okay, and then let's round this one to the nearest whole number. And I want you guys to start part C. I want you to do all of part C, but at the very least, let's set it up, okay?
Alright, and then, Cameron, what'd you get for part B?
Yeah, great. Okay, so if we're rounding to the nearest whole number, we can round to 130. 129.7 is great. All right, and then when you are starting part C, you are trying to find when the coffee will cool to 90 degrees. Okay, so that means your final value should be 90. Okay, you're trying to find when, which means you are trying to find the time. So if you look at your model above, you are using that same equation. Again, don't add these together first. Your first step is always going to be to move over anything added or subtracted to the exponential function. And then from there, we divide what's in front. Like I said, at this point, like we should know, hey, this is my next step. I'm going to be taking the natural log. So if you want to write that out as you're doing it, that is fine. Okay, those are going to cancel. And then you are going to divide each side by this decimal. So if you want to put the quotes underneath and then just put it on this side so I can see what you're dividing by, that's fine. So it's 4, 10, 49 that you're dividing by. Okay, let's round to the nearest tenth for the minutes here. So the natural log of 5 divided by 125 divided by negative 0.04, 10, 49. Okay, also, if you're getting a negative answer here, just double check that you put the negative here. You would only get a negative unit of time if it was something that was warming up, not cooling down. And then include your unit of time, okay, because this one is for minutes. Okay, so anytime you're doing those sort of problems, we're going to include our units. Okay, the pH scale is something else that we can apply logs to. So in one of your science classes, you may have talked about the pH before. If you analyze the pH of a substance, if it's greater than 7, we can classify it as a basic solution. Okay, and if it's less than 7, it's acidic. So what we're going to do is we are going to calculate the pH using an equation from Mr. Sorensen here. So he proposed a more convenient measure to find the acidity of a solution that is tied to its hydrogen ion concentration. It's actually very simple. It's the negative log of the hydrogen ion concentration. So that symbol, that H plus, that is the concentration of hydrogen ions that's measured in moles per liter. Okay, so the hydrogen ion, this should say concentration, in a sample of human blood was measured to be 5.41 times 10 to the negative 8th. We are going to find the pH and we are going to classify as acidic or basic. Okay, so the pH can be calculated by doing the negative log of this hydrogen ion concentration. Do you guys know how to put the scientific notation in your calculator with an E? Do you know where the E button is? It's this double E here. That will do the scientific notation for you. Of course, you can just do the times 10 to the negative 8th. But if you want to use this E button here, you can plug it in. Okay, so if we round that to the nearest tenth, it'll be 7.3. Okay, so 7.3 is greater than 7, which means it is basic. intensity of sounds. Okay, so on this decibel scale, the ear is sensitive to an extremely wide range of sounds, and we have a reference intensity. So I sub 0 is 10 to the negative 12. This is the threshold of hearing, so it's a sound that's just barely audible. It's measured in watts per square meter at a frequency of 1,000 hertz. And then your intensity level is given by the following equation. So we call this intensity level B. It's measured in decibels. It's defined as B equals 10 times the log of the intensity over your reference intensity. And we're going to do this without our calculator. We don't need it. We can do everything with bases of 10. So they give you that I sub 0 is 10 to the negative 12. In example 5, we're finding the intensity of a jet engine during takeoff if the intensity was measured at 10,000 watts per meter squared. Okay, so if we're doing that without a calculator, we're going to rewrite these with the same base of the log. Remember, if you don't see the base of the log, what is it? It's 10. So we have 10,000 as our intensity. This is our I value. Our I sub 0 is 10 to the negative 12. So if I rewrite 10,000 as a base of 10, what is that? 10 to what power? 4. Yeah. And if you have the same base and you're dividing them, what can you do with the exponents? Subtract. What's 4 minus negative 12? 16. This is what you're doing, right? 4 minus negative 12. So it would be 16. So if you have 10 to the 16th, the log and the 10 are going to cancel. What happens to the 16? That'll be your power law, so it will go in front. So your final answer will be 160 decibels.